A chemical change would be a candle.
Hello.
A candle burning.
Candle burning wax into yes. Candle wax burning is a chemical change. Howdy. 10:36. Hi, Hannah. Hi, Janis. Lorelei. Hello. Let me get this straight. Hi, Rhea. Hi, Micah.
What can water be changed into? It's nitrogen.
No, Benjamin. Water is hydrogen and oxygen. Hi, Justine. Okay. We're just at the mark. We don't have to start right away. Just first off, hello, and hope you guys are still hanging in there and doing well, and nobody's sick and all those things. And if you are not feeling well, I hope you feel better soon. I proposed that today we would work through the 2013 free response, and I was hoping to get some feedback. Is that a good idea to work through free response problems? We did that last time at our last meeting, and could be good practice. Let me know what you think, whether that makes sense. Great idea. Good. Sure. Okay. Yes. Okay. Cool. Okay. Yep, sounds good. Okay, sweet. All righty. So, let's get started then on the first question. If you have it there, great. If not, I'll at least hold it up for you to take a look at the problem. So here's the free response 1. There we go. We have a long cylinder of a non-conducting material which is carrying a charge that's evenly distributed. Okay, that's our idea, and they call it long. No, they call it very long. And again, that's AP as physics code for effectively infinite. So let's make a drawing of that situation where we are. Hi, Claire. Hi, Adam. So we have a cylinder. Oh, we have an empty marker. All right, let's see if this one works. The red one's always, I think this red one's been great. I need to get new markers, I think. Okay, so we have a cylinder. There we go. And they're telling us that the radius, that the kind of there's a, there we go. That's the axis. And then it comes out the other side. And they call that the axis. Okay, well, whatever. So axis, okay? They just call it the axis. Fine. And this radius right here is capital R. And just a tip, when they do stuff like capital R or capital Q or something like that, you always have to keep in mind they're probably going to ask something about, you know, expressing something in terms of the variables that are given. So you have to watch out whether you use capital R or little r, because our equations normally have little r in them. You might have to replace something in there with capital R, just a tip. So let's take a look here. They have a density here, charge density rho. And of course, what does that mean, charge density? Charge density means how much charge per volume we have, not how much mass per volume we have in this case. So that would be Q divided by V would be that. And just as a reminder, we also have linear charge density, which would be Q per L. And then we also have surface charge density, sigma, which is just a little sigma, which is Q divided by A. Okay? We use the Greek letters rho, lambda, and sigma for densities, and rho is volume density, lambda is length density, linear density, and sigma is surface density. Okay? So we have that much charge in here, and they're asking us to find, based on this, what the electric field looks like. Now, this is a long charge, basically, an infinite charge distribution, and a linear one. We did that in class, and we know what the case is in terms of the overall picture. So if we have an overall picture like this, where let's take a top view of, and we're just going to think about it as just of the linear charge, line of charge. That's going to be awkward here. Of charge. Okay. So if we imagine just here's the charge distribution here, and the field will look like what from this point right here. So we've got a top view of basically here's our wire of charge coming towards us, going into the board, and what does the charge, what does the electric field look like? Okay, just a reminder about that. Is it going to be like rings, or is it going to be star-shaped, or what does it look like? What's your intuition tell you? Or you remember it? You guys still there? Too much participation? Star-shaped. Thank you, Hannah. All right, so it's going to look like this, assuming it's a positive, right? We're going to expect something like this. That's the top view, okay? And from the side view, okay, from the side view, it looks something like this. Here's our long wire. Whoa, we're kind of coming off it. So we're just going to stop right there because we're going to run out. Here we go. The side view would be that it's going away, but it's relatively evenly spaced. There's no preferred place on there. So that will be something like that. So let's go down a little bit. Good. And to find that, we used Gauss's law. Let's put in a couple more errors just for fun, but they should be evenly spaced. So these are the two pictures you should have in mind. Okay, good. So we use Gauss's law to get to that result in order to find how the electric field looks. Now, if we look at this whole thing, they've got two questions for us. In part A, they ask for us to find the electric field inside, fine. And then after that, they ask for the electric field outside. Okay, so let's think about those. And we're going to start by actually doing what I think is the more difficult problem, because that's the order they're asked for. They asked for the electric field at a radius r. So let's go all the way over here. Hang on a second. I'm going to actually take this dotted line in there. Here we come out. So we're going to look at some location here, which is a radius r. That even show up? That's really small. Gonna switch maybe to a darker pen and maybe a little bit bigger radius. Oh, that's not darker at all. Let's try blue. Oh, that's crap as well. Okay, I know what I'm ordering from Amazon. Okay, so we have, here we go. This is good. This is a radius r away. And we're asking at this point, a distance r away from the center with r smaller than little r being smaller than big R. What is E equal to? Okay, good. So at that point, we got to think, okay, well, what's the symmetry here? And the symmetry is spherical or cylindrical? Spherical or cylindrical symmetry for this thing. Kind of making a look at this, looking at this. What are we looking at? Spherical or cylindrical symmetry? Cylindrical, good. So that means we should be looking at a Gaussian surface that is also cylindrical. Okay, so we're going to put in a Gaussian surface of that radius r. And we'll make this thing go over there. Does that show up? Not really, right? Okay, so there's our Gaussian surface. It's a cylinder. Hi, Octave. Thanks for coming. So that's our cylinder for our Gaussian surface. And we'd like to know what the electric field flux there is. Now, we have three surfaces to a cylinder, three surfaces. We have the ends and we have the sides. So where do we get flux from the electric field that is generated by the charges inside? Are those charges inside generating flux that goes through the sides and the lids? Just the sides? Just the lids? Where are we getting flux? Just through the sides. Thank you very much. So the flux is just through the sides, okay, and not through the top or bottom, okay? That's good, and we can now implement that because, of course, inside still, the electric field will look, and we're just going to draw in a little bit, it comes out like this, right? And that's basically why the electric field will not pierce the end caps. So there will be no electric flux through the ends, but only through the sides. We can apply Gauss's law. Just a reminder what that is. We have to integrate over the whole Gaussian surface, E dot dA, right? And that's going to be equal to Q enclosed. I like using a capital one like that, or like that, divided, whoa, that's misspelled, closed divided by epsilon 0. Okay, working out. Super. So the nice thing here, this is just E dA. It's constant, the electric field. It's not varying over that surface. Okay, so it's pretty straightforward. It's just E times the area of the side. And that's equal to the enclosed charge. Now, the enclosed charge, we can come back to our little relationship between the charge density and the charge and the volume. So charge density times volume, well, that will be the enclosed charge. Okay, so this will be rho times V, and the whole thing divided by epsilon 0. Okay, good. So now we need to put in things like, oh, okay, how big is the side? Now, here's the point you might screw up. The side of this shape has a radius little r, not big R. So you got to watch out with that. It has a radius little r, and that means its area is the circumference here times the length right there. And you might be worried at this point, like, oh man, I don't know what that length is. That's okay. It'll cancel out. It must cancel out. So this we'll call L. Okay, and we'll say, okay, the side has a 2 pi r times L area. Okay, and we can do the same thing out here for the volume. rho divided by epsilon 0. Then the volume of a cylinder is the base of any, what do you call them? Tetrahedron? Okay, anyway, so any kind of shape like this has the base times the height. So that would be pi r squared, pi times r squared times the height, which is L, and that's showing up okay. Good. So let's take a look. We've got a nice equation here. We can cancel some stuff out. There's a pi on each side. I like pi, if you can't tell. So then we have r there, and that cancels out that cap square there. And then the L does cancel out as it should. And then we can sort and rearrange to get our correct answer to part A and do our little victory dance that we got our first answer correct. E is equal to rho r divided by 2 epsilon naught. Rho times r divided by 2 epsilon naught. Good. There we go. All good? Super. Now they ask for us to find the electric field outside as well. And we do have a little room down here. So I'm going to, it's actually, okay. So outside, we're going to choose a bigger Gaussian surface, but in principle, it's the same idea. Let's draw our bigger Gaussian surface over here. Yellow, always the perfect choice. Kidding. Okay, let's use green. So we're going to use a Gaussian surface like this. Oh, this works. Okay, so now we're looking, that's showing up, not really that great. So here's the end cap side. So this is for part B. And the other Gaussian surface in blue was for part A right there. There we go. So same idea as we just did. Okay, it's showing up, but barely. There we go. Okay, good. So this is part B there. And for part B, we can do the same thing. Again, the electric field is the same kind of shape as it has here. So we've got electric field coming out this way, piercing this surface, but it's regular, and it's coming out this way as well. There we go. Okay, so then let's keep going here, and we're just going to do the same thing. This is not for r greater than r. R greater than r, that's hilarious. A little r is greater than capital R. And we've got our equation here for Gauss's law. Integral E dA equals Q enclosed epsilon 0. Okay? And we're going to not rewrite that, but go to the next step right away. So we do have a constant electric field. Fine. And we do have A side. Fine. Again, the end caps do not get any flux because the flux is shaped like a star outwards. So our, at this point, our Gaussian surface, if we took this view over here, and this is still showing up, would be kind of a top view, would be like this. Okay, there we go. So obviously it's going right out there. It's perpendicular to the surface, BT dub. We have a dot product here so that the flux, if it goes perpendicular to the surface, remember the direction of dA is in perpendicular to the surface. So that means we don't have to worry about the angle because cosine 0 is 1. So E times A side, and on the other side, we have rho times the volume. And now we have to watch out. Volume here is something specific, namely, we're not going to be adding up the total volume of our Gaussian volume. Oh, color, this will be good. So this is our green area of our Gaussian surface, whereas the volume, where the density of charge is distributed, is just in the red thing here. Okay, so this is the red volume, not the green volume. And then divide by epsilon 0. And we got to pay attention to that because this is going to be the most common mistake in this, is messing up the little r and the big R. That is not very good showing up. I don't like that pen. There we go. Okay, so let's put things in. I'm going to just scooch down just a tab. So I get one more row, and then we'll finish this part B, and then I'm going to take a picture and all that stuff. Okay, so E time, we're looking at the area on the sides. It is, now looking back up here, that's awkward. So up here, the area of the side is little r, which is the whole radius. I need to draw that in. This is little r, and the other radius, this radius, is big R. It's weird because little r is bigger than big R, but you got to watch out for that. So the area for the side is, again, the circumference, which is 2 pi, watch out, little r, good, times the height of the side, which in this case we call L again. It'll cancel out. It doesn't matter what it is. On the other side, we have the red volume. So density times the volume of the red area, which is, again, the base, pi times capital R squared times L, whole thing divided by epsilon naught. Good. And then we kind of come down here and we look what kind of cancellations we get. The pi cancels. The little r stays this time because we don't have a little r over there. We have capital R, but the L cancels, should cancel, and it does. And then we're good, and we get our answer. E is equal to rho r squared divided by 2 epsilon naught, and then we get an R here. Rho r squared divided by 2r and epsilon naught. There we go. And we've solved part B of the problem. Okay, any questions about A or B so far? You guys still there? You got 12 people still there, according to the list. Okay. Is it okay? Make sense? Yes. Okay. Am I going too fast, too slow, just right? All good? Okay. Good. I will take a picture then. It's good? Okay, it's good. Okay, I will take a picture of the board that I will post later, and then we'll move on to part C and so on. Wow, this is really professional videography. Okay, so let's take a look. So I will just summarize our answers up here because we'll need those in a minute. So I'm making sure I had that correct. I had for part A, this is for R smaller than big R, we have the electric field is equal to rho times R divided by 2 epsilon naught. And then for part B, we had E, this is for R greater than R, R little r greater than big R is rho big R squared divided by 2 epsilon naught R. Thank you. Got that. All right. Now let's take a look at question C. In question C, they now ask us to sketch this. Okay. All right. So we're sketching this, and let's actually put it over here. I don't think it's that tricky. Okay. So we're going to draw it in for the electric field like this. I'm not sure whether you got positives and negatives. I think they're just trying to make you worry about it, whether it's positive and or negative or something changes directions. But it's one kind of charge, okay? So if it's one kind of charge, then the electric field will always point in the same direction. We're assuming it's positive charge, then it's always going to be away, and we'll call that positive. If it's all negative, it's always going to be towards. So then it's going to be in that direction. So I'm not sure what the plus minus thing means. Okay, so we've got that there, and we've got, they're specifically thinking about two things here, R and 2R. And let's take a look at our expression. Now, our electric field inside has this relationship. It's rho R over 2 epsilon naught. Now, you guys sometimes have trouble distinguishing between what variables are and what constants are. What is the variable here? There's only one. I'm actually accidentally pointing right at it. Good. Okay, so R is the variable. And if we consider everything else here, rho, 2, epsilon naught, everything else is just a constant. That means if we think of E as E of R, it is simply a linear relationship. Okay, so that means at value at the beginning for R equals 0 is 0. Good. And then it increases linearly to some value, and we can put that value right there and say it's going to be a straight line like that. And we can say, okay, well, at this point, and we can put the value in, if we plug in big R at that point, it's just going to be rho capital R over 2 epsilon naught. Rho capital R over 2 epsilon naught. So there we go. We've done that part correctly. Now, if we take a look at the other relationship that's valid outside of that, you have a tendency to think that a relationship that depends on the distance from something like this is follows, and I'll give you two choices. Either inverse is option 1, or option 2 is inverse square. Okay, say which one it's not. This is not, I'm accidentally pointing at it again correctly. So this is not an inverse square. Instead, it's just inverse. That means if we're going from R to 2R, the amount of electric field is cut in half, not cut in 4, which is what you might be thinking. Okay, so put that value in. It should be half of that, and where it should be at that point. And then, of course, it asymptotically goes to 0 after that, and should be kind of decreasing. There we go. So, good. There's our solution for the sketch. Looks pretty good. Happy times. And good. Let's keep looking. Part D. Derive an expression for the magnitude of the potential difference between R equals 0 and R equals capital R. Okay, so Okay, it is positive charge. Okay. So let's come, this is part C. And now comes part D. And now we're asking for the relationship between, good, not inverse squared, correct. So for part D, we're looking for reminding ourselves about the relationship between electric field, right, and potential. Okay, we write this down a lot. Okay, equals minus dV dr r. That's the general expression. But because of the nature of the beast here, in terms of our integration path, is going to be always in the direction of the electric field. So we don't have to really worry about the vector quality too much. And we can just rewrite this as that delta V is equal to minus the integral E dr. Good? Makes sense? That's all we're doing here. And we also are remembering that we're at the conventional definition is that V of infinity is equal to 0. Okay? That's the traditional definition. Okay, but we don't really have to do that because they're asking us just to find the potential difference between r equals 0 and r equals capital R. We could use this, if necessary, to find the potential anywhere. Okay, we could do that. We're not going to have to do that because all they're asking us is to find the potential difference between the center and the edge. Okay, so let's just plug it in. So delta V and it's equal to minus integral. And now we're going to integrate from 0 to capital R. Good. So we're going from inside to the outside. So that means, of course, that delta V is defined as V of R minus V of 0, right? Because delta V is final minus initial. Delta anything is final minus initial. So if we integrate from 0 to capital R, delta V is V of R minus V of 0. Capiche? So let's take a look at that, and we'll find when we plug in E, well, we're using R is smaller than capital R. So this relationship, rho little r divided by 2 epsilon 0 dr, that's an easy integral for us, even for us not so calculusy people. And to make that clear, we're just going to pull all the constants out of the integral, which is rho, 2, and epsilon naught. So we have rho divided by 2 epsilon naught. And then our integral from 0 to capital R is just r dr. Hardy har. Ha 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 ha. Sorry. Okay. Okay. So let's go over here and continue this process. We're bringing this back over here. So we have minus rho divided by 2 epsilon 0. And now we're going to get this integrated. Integrating r is integrating to r squared over 2. Move this up. There we go. And we've got r here and 0 there. And plugging capital R, that's r squared over 2. And plugging in 0 gets 0. Okay. So the answer is minus rho r squared divided by 2 epsilon naught. Actually, 2 is 4. Sorry. 4 epsilon naught. Good. There's our answer. So what do we have here? Okay, we have V of R minus V of 0 is equal to this. This is delta V, tiny bit. There we go. So, so we have the answer there. Good point. So now it's on there. So that's delta V. So that's the answer. And looking how they phrase the question, they're asking for the magnitude. Okay. Well, that means that the magnitude delta V is just leaving off the minus sign. So it'll be rho r squared divided by 4 epsilon 0 is the answer they're asking for. Now, but realizing, I believe, I haven't checked the rubric, we're insane, but not completely insane. I believe that if you leave the minus sign in here, we'd still give you credit because that just seems cruel and unusual punishment to, hit you there for the minus sign. But then again, maybe we did. I don't know. I'm going to hope the minus sign is acceptable because that would just be awful. Anywho, where is the solution? I'm not looking. I am looking for it. Oh, it says leaving the answer minus rho r squared over 4 pi epsilon naught is also acceptable. Okay, now we're looking at this. This is negative. If this minus this is negative, well, that means that v of 0 is bigger or smaller. If the difference is negative, then what's true of these two numbers? V of 0 is bigger or smaller? Bigger. Yep. So V of 0 is bigger. And how do they phrase the question here? At r equals 0 is the correct check mark. So we can summarize this as V of 0 is greater than V of r. There we go. Good. All right. Any questions about question 1? Okay. Cool. We only have 10 minutes left, but we did get that question done pretty well. I'm going to take a picture and then erase that. Okay, I got the picture. And I'll scoot you back up. Hello. All righty. So let's see how far we get. Correct. So Giannis's question was, do we have 15 minutes for that problem? I don't know how this is working because they've got kind of, I don't know, they're 45. I'm not sure what they're doing. So because the test is different, but at the normal AP exam, you get 45 minutes for 3 free response questions. So you would have on average 15 minutes. That's correct. And that's difficult. And the overall process is difficult. But remember, the ceiling is high. Very few people score extremely high. And if you decide to just completely skip one problem, not a good idea. And you ace the 2 other ones, right? 2 out of the 3, that's 2/3. That's going to be a 5. So you don't have to complete all 3 problems perfectly. You again want to gather points. And I'm assuming the same thing applies for this year's exam, although there are slight differences, obviously. And also, we're going through it slowly. We're explaining things, and hopefully, when you sit down and you knock it out, rather than have a conversation about, oh, we're going to use Gauss's law and all that stuff, you just write it down and throw things on the paper, and by then, hopefully, you'll be able to do it. Great question, Rhea. I have no idea. I do hope that they will treat you people with grace and understanding. They also have very little possibility of baselining this, how to compare your results to other people's results, because this is an unprecedented situation, giving people 45-minute tests at home. Testing conditions are different. It's difficult to get an idea. They have no multiple choice to kind of calibrate the results. So it's difficult. And I don't know the answer to that question. I'm assuming that the curve will be, they'll try to make it fair, not just for you, but also for the students that took it last year and the students. And, part E. Thank you, Hannah. All righty. Here we go. the non-conducting cylinder is replaced with a conducting cylinder of the same shape and same linear charge density. Okay? All right. That's a little schnickelig. And it's the reason it's a little schnickelig is like, you're like, linear charge density, where's that coming from? So they're saying basically that per meter it has the same charge. So they're switching from a situation like this where they had a solid distribution. I'm going to kind of do it like this. This is like a solid charge. Okay. Now they're going to switch it from this non-conductor or insulator to a surface. Ooh, color change. Let's make it blue so it looks metally. Okay. So it is now a conductor. So instead of having the charge distributed everywhere, including inside, for a conductor, where does the charge go? Something we know. Where does the conductor, where in the conductor is all the charge? Even if it's a solid conductor, it's not a conducting shell, but it's a solid metal tube, all on the surface. Exactly. So all the charge is on the surface only. Okay. And the other thing we know is that inside a conductor in equilibrium, in a static situation, after everything has been said and done, how much electric field do we have inside a conductor? Okay, I'm not sure why you guys aren't answering. Inside a zero, good, good. Now, how about the potential? Is the potential also equal to zero, or is that wrong? It's wrong. What is true is because E, right, just a reminder, is equal to dV/dr. So there's no change in the potential inside. So V is constant inside, whatever value it is. We don't have to worry about that right now, but you have to, this has to pop into your mind right away in this situation. So how does that change for our specific idea for E? They're now asking us to make a sketch of the electric field, whoopsie, electric field versus R. And we're going to have the same idea here. Here's R, here's 2R. Okay, and what's going on there? Well, we now just decided the electric field inside is zero. Got to put that in. Okay, now let's think about outside. If we go outside the radius R, big R, is the situation for the electric field there looking inside, is the situation same or different at this point? Correct. Exactly. So outside, if we were to make a Gaussian surface, it would just be the same situation. Here, the Gaussian surface was like this shape, right? Here, the Gaussian surface is that, but everything's the same. We have the same amount of charge inside. So therefore, the electric field will still be the same. And outside will have the same relationship. It'll again start with the value that we had just a second ago up here. Okay, boop. It'll drop to half that there. Okay, and then it'll go down from there. That's such. And at this point, you got to remember, Oh man, what's going on here? Math people would put like a dotted line here or something like that. Be like, this is not good. Our electric field is not continuous. But that's okay. Okay, and we just remind you about those facts due at that point as well. E can be discontinuous. And why can it be discontinuous? Because V must be continuous. Okay, but it can be not smooth. Okay, or differentiable to be all calculusy about it. So V in general must be continuous, but can be not smooth or not differentiable. Therefore, the electric field can be jumpy or discontinuous because V is not necessarily smooth. Okay? Good. So we were just able to finish one question in 45 minutes, but we were very careful and deliberate about it. And remember, this is not simulating what your experience is going to be like in the test. We're still learning how to do it. And I want to encourage you that when you get into the test, doing all this practice will help you be able to do it and hopefully complete it in 15 minutes, because most likely you'll be like, bam, Gauss's law, let's go. Hopefully. That's my plan. Okay, we're at 11:22, and this brings us to the end of the day. Oh, that's a good question. Yeah, Justine is not here, I think. So maybe we need to ask her about that. So that'd be kind of fun. We could have a joint food day and eat food together, maybe on Zoom or something. Yeah. So we should have a hangout day sometime, just maybe on Zoom rather than on YouTube, and then we can all eat waffles together. Okay. Alrighty. Nice seeing you guys. I'll see you tomorrow, 7th period, 13:25 to 14:10. And until then, hang in there, keep working, go team, you rah rah rah, you rah rah.